Hello, everybody. We're going to start with the problem that we will use to solve some of or explore more about the pressure changes in Aspen Plus, which by this we mean the pipelines, the pipes, and pumps, and other units, of course. The problem that we're going to talk about is about the piping system. So it's used for distributing water to different places, and it is composed of pipe arrangements used to distribute water in different points. All water is pumped by pumps. So we have pump in the very beginning, and then the water is distributed in pipes by splitters. And we have some details about the pipe network, which is we have a pipeline in the beginning, and then a pump, and then the flow is split after the pump into two pipelines, and each pipeline is split into two pipelines. So we'll have, at the end of the day, we have seven pipelines and a pump. And this is going to be useful to because it's going to enable us to define the pipelines with different ways and see how can we define the pump. In this video, we're going to start with the very first one, which is T1. And this is the first pipeline that feeds the pump. And we know some details about the feed, the specs, the flow rate, and the temperature, the pressure, and its composition. You'll notice that it's all water. We don't have anything else other than water in this system. We have some details about the splitters. It's not the point now. And we have the details, which is the important in this video, is the T1, which is the pipeline. We have the inlet stream, the outlet stream names, and the coordinates, and this is kind of important thing that we're gonna discuss shortly. And this is how we will go into the definition of the pipeline. Let's take it step by step. We'll just need to start the file, define the components, the thermodynamic package, and define the feed stream, and then we'll go to the next step. So the only component that we have here is water. It's a well-known material, and then for the methods we will have we need to find out which method that we need to use, and of course you think of water as a polar component or a polar compound, and so we will think of the activity coefficient models either in RTL or Unifac or Uniquac, whatever. But actually we will if we look at these the method filters, you would find out that there is something that's called water, and this is for water and steam only. And this is kind of going to be the most accurate method to use, and this is kind of a specific case for water because it's a very well-known material. It's used in almost all the systems that we deal with. And that's why it's studied extensively, and that's why we have the steam tables, and we have already all the thermodynamic properties tabulated in all combinations of conditions. We will find here that this is water, and you need to pick any one of the steam tables. It's either steam table or steam NBS or thermodynamic properties of water, and these are different kind of systems. I don't think it's gonna make a difference in our case because we are gonna be working in very mild conditions. So now we're done with this part, and then we can go to the simulation, and we need to start by defining the feed stream, which is stream number 1. And we need to see what conditions that we need to have in this stream. We need to have the 0.0072 meter cube per second, the 25 degrees Celsius, 450 millimeter water, and we will see that this is not the units that we're using here, and there's something that we said before to make our life easier. is we can pick from the unit sets that we have. So if I use the SI unit, it's going to be Kelvin, Newton per square meter. It's not the system that I'm interested in. Meter Celsius bar would be the most the closest, but it's not actually the one that I'm looking for. So I can create a new unit set. I can call it new, for instance, and I'm gonna take the meter Celsius bar and do the changes. So I have the temperature in Celsius. This is what I need. I need to have the pressure in millimeter water. It is millimeter water. The delta P is gonna be in millimeter water. Delta P height, that's okay. And we have the temperature in Celsius, the flow rate, the volumetric flow rate. I want it in cubic meter per second. And the cubic meter is named here as CUM. It is cubic meter per second. Is cubic meter per second. So this is the default units that we're gonna use. So now I can go now and pick the new unit set that I am using, and we'll find out that this is Celsius, this is millimeter water, and this is it's not working. No, it's not work. Oh, it's volume. No, I don't know why it's not doing this. It's not changing for some reason. I think it is kind of frozen. It is standard volume. It should be. I don't know. Something is not right about it. I'm gonna close it and reopen it. Maybe we can have this problem fixed. Oh no, so this is the standard volume and it's cubic meter per second. Sometimes this happens, so it's not something that you need to like freak out when happens. This is 25 Celsius, 450 millimeters water, the standard volume 0.0072, and this is the mole fraction. It's gonna be 100% water, and now we're done with defining the feed stream. And now for pressure changes, we'll go to the pipeline, and again this is gonna be the core of the work of today. So I'm gonna call it T1 as it is named here, and we'll define the outlet stream, which is stream number 2. And now comes the interesting point. We need to define the pipeline. And the pipeline, as we see here, it is consists of 3 nodes. And we have here the coordinates, and we know the diameter. But to understand what do we mean by this, I'd like to first look at this figure. So in this figure, we have a pipe or a pipeline that is moving horizontally, and then it ramps up with an angle of 36.87, and then goes back to horizontal for 4.5 meters. I have this is 3 meters, this is 4 meters, the height is 3 meters, this is 4.5 meters. So what happened here is that the pipeline changed its direction from here to here, and changed its direction one more time from here to here, and we will assume that it is the same diameter. And we because of the change of the angle, we call this a node, and this is a node. So the node is a point where the pipeline changes one of the properties, either the inclination angle or the diameter of the pipeline. And this change will have an effect on the change in pressure in the pipeline, and that's why we cannot deal with this part as we deal with this part. So this part is called a segment. This is a segment, and this is a segment. So we have here 3 segments. And two segments are separated by a node. This is a node separates two segments, and this separates two segments. And there is the node in the very beginning and node in the very end. So to be able to define the pipeline, you need to define it by one of two ways. And this is what is mentioned here. You will either enter node coordinates or enter segment length and angle. So this is the segment geometry. So you can do the coordinates, and by the coordinates I mean the x, y, and z coordinates. So I start here by the datum is gonna be 0, 0, 0. This is x equals 0, y equals 0, z equals 0, and this is x. This moved in the x direction for 3 meters. Didn't change the y and didn't change the z. Z is gonna be perpendicular this in this direction, and y would go into or outside the screen. I didn't have any change in the z direction or in the y direction. I only had change in the x direction, and that's why this node is gonna be 3, 0, and 0. To move from here to here, we see that the z changed by 3. So we have here the value of 3, and we have here the value of 7, because it is 3 meters, and we added 4 more meters to the 3, so the total is 7 meters. And the same here, we added 4.5 to the 7, so it's 11.5, 0, and 3. And this is how we can define the coordinates, and the coordinates will include all the information about the change in the elevation or the length and the angles and everything. So once you define the coordinates, you don't need to define anything else. Or you can say that I have a pipeline that consists of 3 segments. The first segment, length of the first segment is 3 meters, and the angle is 0. The angle between this pipeline and the horizontal line, the floor. So by doing this, I define the segment by two pieces of information: the length and the angle. Here the length is gonna be 5. This is 3, 4, and 5. This is right angle triangle. So this is gonna be 5 meters, and the angle is 36.87. And this is gonna be 4.5 meters, and the angle is 0. The angle is the angle between the pipeline and the horizontal line. It's not between this and the previous pipeline or the previous segment. It is between the pipeline and the floor or the ground. So we can do both, and though both things will do the same or will deliver the same pieces of information. So here we have two options: either to go for float flow or for solid conveying. If you go for solid conveying, then you do like a totally different thing. It's gonna be either a pneumatic transportation or something like this, which is gonna be totally different from the float flow. For now, we will go for float flow. And for the directions, either you calculate the outlet pressure or the inlet pressure. So you define one of them and calculate the other. In my case, I need to define or calculate the outlet pressure. We can have thermal options by doing energy balance with the surroundings, but if we do so, we have to give more information about the heat transfer coefficient and other information. So if we do this, you'd see that this will require more details. But in this case, we'll just go for the temperature profile, either the linear temperature profile or constant temperature. I'll assume that there is no change in temperature while the flow is or the liquid is flowing. For the segment geometry, we have already talked about this. The property calculations by doing flashing in each step. Um, by doing flashing in each step is what it does is called the rigorous flash. It does the calculations by breaking the pipeline into segments, and each segment you do, or the software does the calculations of the or the flash calculations. Um, uh, the property grid is gonna be different. It's more like a shortcut method. It does the calculations by doing some interpolations instead of doing the rigorous calculations or the detailed calculations. The flow basis is based on the inlet stream flow or the outlet stream flow. I know the inlet stream flow, so I'm gonna use this. You can specify the inlet conditions if it's different from the feed stream. If you don't specify them, it's gonna be taken as the feed stream conditions. And here comes the point of the connectivity, and here we are gonna define the pipeline. The information that we have is, I think we can put them side by side so you can see easily what is the conditions. Let's try to fit them together. Yeah, so this is the first one. It's gonna be, you have to define the inlet node from node 1 to node 2. This is the node 1 and node 2. And here I defined this or said I'm gonna define it by the length and the diameter, but this is not what I need to do. I want to go for the coordinates and do the connectivity. And we can edit it. The diameter is gonna be 2.5 inch. And this is the roughness and which is the height of the roughness in the surface of the or in the internal surface of the pipeline, and it's very important to calculate the friction factor, and that's why it's taken here by default with this value. We will do the coordinates of the first one. It's gonna be 0, 0, and 2.71, and of course we need to keep in mind that the units are important. So if I don't change or I don't have the proper units, it's gonna be a big problem. And it goes to 1, 0, and 2.71. So this is it's now done, and we can add one more node, which is node number 2. One more segment, and the segment from node 2 to node 3. And it already takes the outlet conditions of the first segment as the inlet of the second. So we have, these are the coordinates that I have already defined before, and it's gonna be 1.29 and 2.71. So this is all what I need to do, just to keep in mind that this is not a very long pipeline. It's just 1 meter and almost 29 centimeters with a change in direction. So I shouldn't expect a lot of pressure losses. So for now we will do the run and just wait and see what is the outlet pressure, and sort of do some analysis to the results and see what can we get out of this. And now it's processing the input specifications. For the first time, it takes some time to get all the calculations done, and this is what we are waiting for now. We will see that there is an error, and this is kind of weird because we haven't done anything, just one simple unit. And if you open the warning, you'd see that the thermal option is required for single component model unless number of phases equals 1 is specified. So it says the calculations will continue with phase equals 1, phase equals liquid. So it seems that there's something that's related to the phases, and this is not something to worry about, but just because this is a pipeline, it has to deal with liquids. So you have to specify that this is liquid only, and if you do that, then you will do the run and the results would be generated without having any error messages. So this is something that you need to keep in mind. Even at very small temperature, like the temperature we are working on, it is something that happened. And now for the result, we'd see that this is the summary. It tells the inlet pressure, the inlet temperature, the outlet pressure, in millimeters water, the outlet temperature, the molar flow rate, and some kind of good information, some information about the streams and the balance. So it's not gonna be that much information, but this is here where I'm more interested in exploring this part. You see that the velocity here is 2.2, which is a good velocity, which usually in the liquid phases we like to or prefer to have fluid flow with velocity of from 1 to 3 meters per second, and this is 2.20, almost 28 meters per second, which is very good. The flow regime is all liquid, and you can see the pressure drop profile from here. And you see that the total pressure drop, there is a pressure drop in the first pipe, and then there is a pressure in the second, and the majority of the pressure drop, or the first part has higher pressure drop here. You see that the pressure in the first part is higher because it's a longer pipe. It's gonna be more better to take a look at the pressure, not the pressure drop. And this is easier to interpret. This is 450 millimeter water, which is the feed pressure, and for the first segment, the pressure decreased to 366, and the second segment it decreased to 342. So the majority of the pressure losses happened in the first part, which is expected because the length of the first pipe is 3 times the length of the second. So the pressure drop will be 3 times because both have the same diameter and the same roughness. And now we can take more or take a look at the profiles here. Again, we have the summary. You can have a look at the velocities. You can take a look at the pressure drops, the flow related, and there are a lot of information that we can find here. So this is almost everything for the pipeline definition. In the second or the next video, we will talk about the pipe, and we'll see how we can define the pipe and the pump. I'm sorry, and see how the different ways of defining the pump and the pump curves and all this information. So I'll see you then, inshallah. Goodbye.